Hello and welcome everyone to yet another session in the Data series. We're thrilled to be here with you this evening for a session full of action packed learning. I'm Sabrina Bashir, part of the data science team at Analytics Vidhya. For those of you who have joined us for the first time, here's a brief introduction to the Data R series. The Data R is a series of webinars conducted by Analytics Vidhya and led by top industry experts. It's a fun way to understand the concepts of data science and AI from the leading players in the industry. And today I bring you some great news. We've launched a brand new initiative of free courses, bringing you the latest in AI education at no cost. Stay ahead of the race by exploring all the trending topics we have added to the list. You can check out our latest free course on building a deep research AI agent, the link of which I will add to the chat section soon. Go check it out. Do join, do learn, and let us know your feedback on it. The recording of this session will be available on our platform 2 days from now. I'll be sharing more details about it during the session. Now, on to today's session, which is Beyond Keywords, a hands on guide to modern semantic search techniques. In this data hour, the speaker will unpack the evolution of embedding models and their role in semantic search. This session will cover the shift from basic keyword search to sparse and dense embeddings, multilingual search, vector databases, rerankers, and advanced retrieval techniques like agentic and cascading search. Through an interactive demo, you will gain hands-on experience and insights into building high-performance AI applications with semantic search. So get ready to soak in some practical knowledge that can enhance your AI-powered search capabilities. Now, before we kick things off, here's a quick recap of the housekeeping items. We are recording the session, and as I mentioned earlier, the recording will be available on our events page, the link of which you will find in the chat section. Please use the Q&A section to ask any questions you might have during the session, and we'll answer them as the data hour progresses or towards the end. We'll be sharing a feedback poll towards the end, which you're all requested to fill so that we can improve our sessions in the future. As we navigate through the content, we'll be sharing useful resources and links in the chat section. So do keep an eye out for it. Now, on to today's speaker. In this session of Data Hour, we have Arjun Patel with us. As a developer advocate at Pinecone, Arjun Patel creates educational content on vector databases, retrieval augmented generation, and semantic search across various platforms. With a BA in statistics from the University of Chicago, he brings extensive expertise in natural language processing, deep learning, and large language models to his role. His professional journey includes data science projects at Spico and Appen, where he contributed to AI driven speech coaching and AI generated content detection. Thank you all for your patience. Now, over to you, Arjun. The virtual stage is all yours.
Welcome to today's topic, Beyond Keywords, a hands-on guide to modern semantic search techniques. This is me. I'm Arjun. I'm a developer advocate at Pinecone, and what we do at Pinecone is teach people how to do different kinds of vector search using something called a vector database. I like to show people this image to kind of concisely describe like what we're really good at and what we help people end up doing. But we'll get into the details of what vector search is and how to implement it a little later. Before we get there, I want everyone to kind of think about this story I'm going to tell you. Imagine you're walking in a forest and a bird flutters in front of you, but before you can reach for your camera, it flies away. You know that it had a red head, you know that it had black wings, and it made a really loud noise on some trees nearby. How would you figure out what it was? In today's reality, we're spoiled for choice in finding different ways of searching for information, especially with images and text. But you can imagine that you might want to construct some sort of query in order to find the image that relates most to this bird that I'm describing. And I have an example of one of those queries here. It's a big bird, it has a red head, black wings, and it's pecking at some wood. That's maybe all we know at the moment. So what happens if we take this query and do a search in a place like Wikipedia? We get some results like this. These are not related to the bird that we were looking at all. And in fact, there's no page that exists that has this keyword query at all in the first place. However, if we implement some more clever techniques using things like re-ranking, dense models, sparse models, and a little bit of data cleaning, we can get exactly the bird that we were looking for back using the same exact query. The difference between this left screenshot and the right screenshot is going to be what you're going to learn today, which is to say the difference between traditional keyword search and advanced forms of retrieval like cascading retrieval. We can summarize this gap as understanding that advancing beyond keyword search means bridging the way between how text is written on the internet, especially in technical documents or even at your organization, and how people think about the information that they're trying to find. So with that in mind, here's the agenda for the talk today. We're going to go through a lot of different things. This is going to kind of give you a foundation in how to think about modern semantic search rather than a rigorous evaluation of how to do semantic search. So I hope that today you'll walk away with the understanding of how to implement different kinds of search and when to use them, and even how to evaluate them. We'll go over what keyword search is generally. We'll talk about how language modeling has created a strong foundation for semantic search. We'll talk about dense models and sparse models, which are two different ways of doing semantic search. We'll talk about vector databases, of course, re-ranking, which is a way to improve the results of an initial semantic search, hybrid and agentic approaches, and then we'll cover some evaluation strategies as well. And finally, I'll show you this demo, which is the screenshot on the right that I presented just a few moments ago. When we think about building search systems, there's three parts that we need. We need a way to represent our queries in documents, which will be done by something called a model. We need a way to score queries in documents, which will allow us to understand what queries are important to what documents. That might be a distance metric or an impact score, if you've heard of those before. And then we need a way to index and search over this information. So when I start to explain like sparse models, dense models, keyword search, I want you to think about these three pieces and like what pieces we're improving on and changing as we're developing these models. Now, but before we get to the more complicated forms of search, I wanted to start at the beginning, which is keyword search. If you were to imagine like the simplest possible version of keyword search, it would be looking at your input query, looking at all of the documents in your corpus, and trying to find all of the documents which have the words that exist in your input query. In other words, you would need a vocabulary. You need to represent every document in terms of that vocabulary using something like a bag of words vector or something along those lines. And then you need to count overlap. Now it turns out that this works like not too bad. Like this works pretty good. Like most forms of search in the past couple of years before the advent of RAG have been this type of search, and they've worked pretty good for people. But there are really specific situations in which this starts to fall apart. And one of the queries in which I showed you earlier is one of those situations. When you have like terminology heavy search that where you're working with experts that kind of deal with that terminology very often, this type of search works great because you know what you're looking for, you just need to find it, and you know the words that you need to find it. But this type of search cannot handle synonyms or related words, which is the problem we call vocabulary mismatch. It can't handle meaning within words within context. So if you have the same exact word, but you're using it different ways, this type of keyword search can't really handle that well. And it also doesn't work that well with asymmetric data. So if you have a question and you're trying to find an answer and the answers are not written like your questions, keyword search is not going to help you that much because your queries are going to be really short, which means the amount of overlap you're looking for is really small, and your documents are going to be really long. So what can we do about this problem? It turns out there are two main branches of search that aim to address different parts of making search better. Sparse models allow you to improve keyword search without sacrificing precision. This means that we're going to place an emphasis on the words we're looking for And we're going to become a little more flexible about how we're finding those words in our corpus. Dense models go in the opposite direction. Dense models expand the amount of queries we can handle because they work on the meaning of the queries and documents rather than the specific words that are being used themselves, which means we can deal with like a wider range of questions or a wider range of formats of search. Both allow us to solve the problems I described previously, which is vocabulary mismatch and semantics. But in order to do either of these things, we actually need a base layer, and that base layer is going to be what a language model is. So in the next couple slides, I'm going to quickly go over how we were able to kind of get language models that allow us to understand what words mean, which lets us address this problem of vocabulary mismatch and semantics. Very quickly, I wanted to start right at the beginning with vectors. So what are vectors? Vectors are a way to represent non-mathematical objects like text or images into fixed size lists of numbers. We can see in this upper right image, we take the sentence, "I went to the park over the weekend," throw it inside something called the vector embedding model. We get out a fixed size list of numbers, which represents what that vector is. And it turns out that if you represent text in this way, and it could be as simple as like writing a bag of word vectors, which means you just take a count of all the unique words in a sentence and you kind of construct a vector that represents that sentence, or it could be something more complicated like the output of a vector embedding model. Turns out if you do this, you can start to do mathematical comparisons on these non-mathematical objects. So in the bottom right of the screen, you can see that we have questions and we have answers that are clustering together in vector space. And we can kind of determine what the answers to questions are based on how close they are in vector space. Now, of course, the question is, how do we accurately represent what these sentences and texts mean in vector space? Well, before we get into how these models work, I want to present this idea from natural language processing that really helps me understand why we're able to do this, really helps motivate the reasons why these models work so well. There's this idea from natural language processing called the distributional hypothesis. And what this hypothesis says is that we can learn about the meaning of words and concepts based on how they co-occur inside texts. So if you think about the word phrase like hot dog, that word is going to be located near other food-related words in the whole world of like corpus documents. But it won't be near space-related words because those words are not close in meaning. Literally, the neighbors of the words help inform the meanings of those words. And if this is true, then maybe there's some property about the co-occurrence of these words and all words everywhere in any corpus that we can take advantage of in order to model the meaning of them using language modeling. And I'll give you an example of a model that has done that successfully. A large language model is basically a neural network that has been trained on billions of data points, which learns the relationship between concepts in natural language. And the important part about large language models is that they convert sentences and queries and text into vector embeddings, which have an encoded meaning, which means they're key for us to kind of step up our ability to do semantic search. The model I want to talk to you about today as a language model example is Excel and Roberta, which was released in 2020. And it was this embedding model that was trained on an internet's worth of data across 88 different languages, which learned how to represent the meaning of words across language. The craziest part about this paper is that they were able to do this using three things. The first was a massive scale up of training data, internet scale data. The second was language agnostic tokenization. And the third was masked language modeling. And by putting all three of these things together, they were able to create a mathematical or a language model that's able to learn the meaning of words across languages. Tokenization allowed these researchers to represent tokens from all sorts of languages in the same language. And the way this is done is by taking some text, breaking it up into subtokens called subwords, and then finding as many common subwords as possible across all languages in the world. It turns out that you can actually train a model to do this because of the way that languages are written on the internet. And the researchers used something called sentence piece in order to create a 250,000 token vocabulary across all languages, which means they were able to understand how to represent all languages and what they looked like. Now the question just becomes, how do you learn about the co-occurrence of all of these tokens irrespective of language? The second piece of the puzzle is mass language modeling. I like to call mass language modeling Mad Libs for robots, which is this idea where you have some sentence, you like this one, I want to play in the park. You randomly drop parts of that sentence and you mask them away. And then you ask the language model, hey, can you predict the words that are missing from this sentence? And this is very similar to this idea of the distributional hypothesis that we just talked about, which is that there are words that occur with other words and we can infer their meaning based on their neighbors. It turns out if you do this at scale across languages and you continually train a model to kind of get better and better at this task, it will learn what words should go where in any given sentence on average. And as a consequence, it will learn really good intermediate representations of what each of those tokens are supposed to be, which we can use as a proxy for their meaning. So by operating on this task, we're able to create token level embeddings, which we can use as a proxy for what those words mean. And then we can start to do math on those words. Now that we have a way of kind of representing what token level words look like, we can start talking about sparse models. Like I said earlier, sparse models allow us to prioritize precision in search by focusing on the keywords that we're using in some query. For a general description of how sparse search works, which again is kind of like an umbrella term for advanced forms of keyword search, we first start to learn the importance of words to a document based on how much they should be weighted in importance to that document. This concept is called impact scores. So with keyword search, we can kind of think of the importance of a given word as the frequency of how often that word occurs within a given document. Here, we're going to try to learn a formula for like the importance directly instead of just having it be the frequency. So what we'll do is we'll look for the keyword overlap between document and query, and we'll weight on the words. Then we'll take those weights, we'll sum them, and that will represent how relevant that document is to a query. So it's not just the direct frequency, it's also the importance and how much that weights and sums into that query. So the question becomes, how do we nicely calculate these weights beyond how often they occur? We need some better way of understanding how important these words are. The deep impact model is a great way of kind of calculating this form of importance, and it combines a lot of ideas from large language models and keyword search to kind of achieve this ability. What deep impact does is that it learns impact scores directly from training data of like queries and document answers. And it leverages two techniques, document expansion and contextualized language models, to solve vocabulary mismatch. They basically train something called an impact encoder and a large language model to learn these impact scores directly on a token level, which allows them to kind of create this relationship that I described prior. How does this work? The first step in the deep impact flow is to solve vocabulary mismatch via document expansion. This is a very interesting idea. The idea is that if you have an entire document set in a corpus, and you're worried about people asking the wrong queries to find the documents that they're looking for, then you should just come up with a list of queries that map to the document that you want people to find and add that to the document. Very simple idea. And then once you've added that to the document, the new document is going to be more likely to come up if someone asks a related question. Now the trick is, how do you do this at scale? So what these researchers did is they used something called T5, which let them generate text that would be potentially relevant to a document, appended that to every document, and create these type of expanded documents. It's a very simple idea, right? It's like, okay, now we have more queries that we can possibly map to. We're just adding the words that we're missing from the document. The next step is going to be this type of learning scoring behavior. So I'll walk you through what this diagram is kind of doing so you understand what's going on. We have this expanded document, which is first going to be passed through a language model encoder. Just like we talked about XLM Roberta before, this language model encoder is going to learn about what these words mean, and it'll output an embedding of the meaning of each of these tokens, which is represented by these kind of intermediate passages here. Those embeddings are going to go into something called an impact score encoder, which is basically a multi-layer neural network. And that impact score encoder is going to try to predict the importance of that word to the document. And those are going to be our impact scores. So we're taking the meaning of the word, which is represented by the embedding, and we're trying to predict the importance or the relevance or the impact of the word to that document. And then we're going to store all this information in something called an inverted index. And we'll use this information when we're doing the querying in order to figure out what documents are important to what. What's an inverted index? An inverted index is a data store that's really useful for keyword search or sparse search operations. How it works is you kind of take a string, you break it up into the tokens, and you store, instead of storing the documents that map to the tokens, you store the tokens that map to the documents and their weights. So when you want to do a lookup of like all of the documents that have these tokens, you can just look up the words, which is way faster than looking up the documents and trying to find the words. And you can go inside and see what the weight of that word is inside of that document. And this will become important because when we do retrieval, all we're doing is tokenizing the input query, what is semantic search, breaking it up into tokens, going into the inverted index, finding all of the documents that have these tokens, summing only the weights of the tokens that exist in the query. This is the idea of the precision coming from keyword search, and then returning this final relevance score by summing these values. Now that's great, but what if we actually don't care about the words? Like what if we're having difficulty dealing with queries that we can't really expect, or maybe we're dealing with non-experts, maybe we're dealing across languages? How can we kind of resolve this issue? Well, if we go back and think about Excel and Roberta, we're realizing that it doesn't actually give us a way to represent documents directly without focusing on the words. It's producing token level embeddings, not document level, which is something we would be more interested in if we wanted to represent the whole concept in the query like we do in dense search. We also need some way of handling asymmetry, which is this idea of queries and documents being fundamentally different. And then we might want an embedding model that takes into account not only the meaning of those documents, but the relevance and the search capabilities that those embeddings impart to things like multilingualism and semantic information. That's when we start looking at models like multilingual E5 large. This was a model that used training data, process, and fine-tuning to create document level embeddings optimized specifically for search across languages. We're going to see some patterns in how multilingual E5 works that kind of remind us of these ideas that I've presented earlier. Now, what dense search is doing is exactly what I described just now. We're kind of creating these document level embeddings so that we can measure the distance between these documents in vector space and the queries that we're using, rather than looking at the specific words. And we're going to find the documents based on that sort of distance instead. And this distance that I'm describing is going to be something called cosine similarity, which measures the angle between the vectors that we're interested in. The assumption here is that the angles that are closer in vector space are going to be more similar, and the vectors that are farther away in vector space are going to be less similar. So this is going to be the way of finding similarity instead of doing impact scores. The way multilingual E5 large was able to do this, the first step was kind of finding these real world pairs. If we think back to this idea about co-occurrence, what these researchers did was exploited certain forms of co-occurrence that relate directly to relevance. So if you think about article titles and their content, these things occur very close together in corpuses, so therefore they should be close together in vector space. Translation pairs should be close together in vector space because they mean similar things, even though they're in different languages. Question and answering documents, the questions and answers should occur close together in vector space. All of these form a good corpus for this model. The second step is kind of a training methodology called weakly supervised contrastive pre-training, which allows them to push close vectors together in vector space, or excuse me, push things that should mean similar things or be relevant to one another close together in vector space, while pushing away things that shouldn't be close together in vector space. And they're able to kind of do this type of training to adjust these token level embeddings to these document level ones, which allow you to find things that are relevant. And we can see that you'll have some query, you'll have the true relevant passage, and then you'll have a bunch of negative ones, and you'll try to move the query and the true passage close together in vector space while moving the query and all the other fake passages far away in vector space. Finally, they were able to fine-tune specifically on tasks that are important for search, like question answering, retrieval, natural language inference, which is kind of guessing words across languages, duplicate identification, which is great for finding similarity, as well as some other clever fine-tuning techniques to kind of get a model that is really good at not only representing concepts, but also finding relevance. Now, quickly, I've kind of like gone over two different ways in which language models play in sparse search and dense search. I'm going to clarify them one more time because it was confusing for me when I was learning. Language models in sparse search allow you to reweight terms according to their meaning and relevance on a term level, whereas language models and dense search are kind of reweighting those term levels documents and pooling them into a massive document embedding, which allows you to understand their overall meaning. So these are the two different methods and those differences in those approaches. So that's great and good, but now that we have that methodology, how do we search over all of these vectors that we're kind of producing? Well, you need something called a vector database, and a vector database allows you to index all these vectors and compare them really quickly using specialized algorithms to find these most similar documents, and that's kind of what Pinecone does. When you're doing semantic search, you end up building an architecture like this, where you have your data sources, you ingest them through your embedding model, you pass them to the API, upload them to Pinecone, and then when you have some query, you kind of pass that back into Pinecone, embed it, find everything inside that's close, and return the results back. That's kind of like where a vector database plays into here. But improving these types of embeddings only goes so far. And the reason for that is because embeddings fundamentally compress information. You're going to lose some aspect of the information of the query and the document using an embedding model, no matter what you do. What's also interesting is that embeddings actually don't take into account all of the documents in the corpus. They're independent. Right? You have one model that encodes these things separately, and then you're trying to find similarity. But it would be really great if we could actually encode the input query and the document together in the same context to kind of understand how they interact with one another. There's also situations in which you might have quality which outweighs latency. So you might really need things that are important and relevant over how long it takes you to find those things. And maybe you need to optimize context, which has become really important when people build things like RAG or large language model-based applications that retrieve context and operate over them. And that can impose a really huge cost. So what do you do in those situations? You use something called a reranker. What a reranker does is it recomputes scores using a query and a document and outputs a new score. But instead of an embedding model, which kind of does the same thing, like, right, taking the query and the document and output a score, the reranker ingests both the query and the document at the same time and produces a score that's contextual on this information. Now, you can imagine this is an expensive operation, so you don't want to do this on every single possible query document pair. It would take forever to do your search. Instead, you kind of do a wider vector search, return a larger set of documents, and then you re-rank those documents using both the query and the document context in mind, and return a subset of those back. So it's kind of like a refining operation. You're taking a massive subset of documents, you're refining them down, and you're returning only the most relevant ones. Now, this is great for large language models and for context optimization because you can do something called solving the loss in the middle problem, which is this idea that if you have too much context, you might miss what you're looking for. If you have too little context, you might not even find the thing that you need. But if you kind of optimize your context, so you have a budget for how much information you can look at, and you're ensuring that that information is the most relevant possible, you can really increase the speed of the processing of these documents and also reduce costs at the same time. And a reranker kind of helps you make that adjustment. So now that we've talked about sparse models, dense models, and rerankers, we have all of the building blocks for an advanced form of search. Now the question is, how do we combine them? We'll talk about a few advanced retrieval methods. One is cascading retrieval, which is the retrieval method kind of talked about at Pinecone. This is also known as hybrid retrieval. This idea is that you kind of combine results from dense and sparse using a reranker. So you have corpus, you find your relevant documents, you pass them to, you do a dense and sparse search across those documents, and then you re-rank them. And it turns out that if you kind of take this approach, you can improve results about 24% compared to just using dense alone, because you're kind of combining both of these things and then putting them in the same relevance space by using the reranker. And I'll show you how to kind of do that or what the results of that are in the demo. There's also agentic retrieval, which is really new nowadays. What this does is it kind of lets you use an LLM to drive interaction with your data store. So Pinecone Assistant is an example of this. We have a product that allows you to kind of ask one query, and then Pinecone Assistant will go and generate queries for you and ping them against a vector database to generate a final response. And this is kind of like query expansion, where you're adding new query ideas to the thing that you're kind of looking for. And all of this does rely on putting together these pieces of re-ranking, sparse search, dense search, so on and so forth. Great. So now we know different ways of kind of combining these things. How do we know what's best for our use case? Well, it turns out that it depends, right? But I can give you some guidelines on how to evaluate these different systems and comparisons in order to build the best system for what you're looking for, which I imagine what many of you are thinking. So here are some guidelines. Sparse search is great for terminology-heavy experts in technical domains like finance, medicine, or when you're dealing with a lot of entities like part numbers, proper nouns, ticker symbols, money, so on and so forth. Dense is great when you have multilingual applications because you can just represent everything in the same vector space and just do search without having to do translation. Domains when there's significant vocabulary mismatch, or when you have asymmetric documents like questions and answers, recommendations, multimodality. Re-ranking works pretty well. So if you're trying to look for a really low impact across domains and how to increase the quality of your results and you don't care about latency that much, re-ranking will most likely help you. So it's almost always important to try. And hybrid search is great when latency doesn't matter as much, but you want as much quality as possible. So you want to review as many relevant results as possible. And when you're dealing with a lot of different query types, so you want to handle both like sparse and dense types of queries, implementing hybrid is a pretty straightforward lift. You're not really adding that much latency and you're allowing more results to kind of be reviewed. Now, when we think about evaluation, business metrics kind of come to mind as like a really great way of understanding how well your models are working. What I mean by this is you kind of incorporate them into a system and then you evaluate the output of that system to kind of understand how well the model is doing at what we're interested in. So in e-commerce, you might have this idea of conversion or CTR, click-through rate. And a Pinecone customer, Hyperleap, was able to get a 50% increase in click-through rate by implementing like a semantic search system, which is really cool. You might think of customer service or support, where you're trying to help customer service agents find the most relevant information to whatever they're doing. So you can have a metric like time to close ticket or resolution rate. We have a customer called Assembled, which kind of builds tooling to help customer service agents find answers faster. They achieved up to a 95% reduction in time to close ticket from 2 hours to 4 minutes, just by implementing really, really good search. You might have technical documents like for a package or a code base, and you kind of need to help people get started doing something with that code base. Then you can measure time to activation, giving that person access to a search tool. And for the type of demo we're going to work today, which is kind of building a bird search database over a corpus of information about birds, I'm going to be interested in novelty, which is this idea of how many new birds can I learn about that satisfy the input query. So how many results are relevant given to my query and how different are those results from one another. Great, so this brings us to our demo, which I'll spin up in just a second. What we're going to do is we're going to build a search engine using just Pinecone as our primary dependency for all kinds of North American birds. So we'll ingest a data set of all the North American birds on Wikipedia, and we'll try to learn about different kinds of search by doing this type of ingestion. We'll use Pinecone for inference to create the embeddings, and we'll use Pinecone for doing the vector search as well. We'll compare how good these results are using mean average position and unique relevant birds returned. Mean average position sounds a lot scarier than it actually is, but it's actually just a representation of how relevant each result is and in what order do those results appear in our returned results. And of course, unique relevant birds is just how many of those results are relevant and how many different birds we returned that are relevant. If you want to take a look at the repository, you can navigate to github.com/pineconeio/bird semantic search. If you'd prefer to see me work with the demo, I'll pull it up in just a moment. All right, everyone's favorite part of the day, a live demo. Give me a second to reshare my screen and we'll get started. Great, so this is a demo. This is running locally. What I've done is created an interface for people to kind of easily learn about and evaluate different kinds of search methodologies. I have some questions that are pre-populated here that we can try to kind of see what happens. The first one I want to show you all is the one that we started with at the beginning, which was big bird, red head, black wings that pecks wood. So I'm going to go ahead and hit enter. It'll take a few seconds to compute all of the queries, and we'll get our results back. We'll go over each of the results and annotate them to see whether they're relevant or not relevant. So this first tab is going to use best match 25, which is just traditional keyword search. We see that this is not actually helpful at all, right? Like this is not the bird that we were looking for. This is clearly different, but we can see that of the words that are being returned, we can see why overlap kind of informs why this is being returned. This is a bird that has some of the qualities of what we were looking for, but does not have the desirable distinguishing quality, which is kind of like the woodpecking behavior. And the third result, we actually do get a woodpecker, but it's not the one that we were looking for. So I'll mark this as relevant and say, okay, this is something that could be useful for us, but not necessarily exactly what we're looking for. I'll hit log keyword annotations, and this will save the results back into the metrics tab, which will let us see how well we did at finding relevant birds. We found one, and what the mean average position of those results were. Let's go ahead and look at cascading retrieval. When we do that, we get back a bird that is a woodpecker, which is cool. And we also get some sort of loud sound that's kind of being returned, which is great. And we can see that this is the top result compared to the one that we were looking at prior. We get some other results here, which aren't necessarily exactly what we're looking for. We get overlap, which is what we were looking at prior. If we look at the dense results, it doesn't seem like we're getting anything interesting there. And with the sparse results, it looks like we are getting another woodpecker, which is great. So I'll go ahead and log this here, and I'll log this here. And now we can kind of compare and see what is keying out and what isn't. Let's try another query. Let's do this one. Birds that are bad at flying. This is an interesting query because we're asking about a negation, almost. We're taking this concept of flying and we're saying, okay, we want things that are not good at flying. There isn't like a good word. There are words that are a good opposite to the word flying, like flightless birds, but those birds cannot fly at all. So we kind of just want birds that are not good flyers. So let's see what the results will be using this kind of idea. Hilariously, the first result under keyword search is wild turkey, but the sentence we get back is he is a bird of bad moral character, which is really funny, but not what we're looking for. This is a sentence about European storm petrels that are bad omens. This is not the kind of bad we're interested in. Passenger pigeons are really good at flying, so we can't do that at all. Same petrel argument, and then ravens, which are kind of bad omens. So you can see the failure of keyword search kind of like peeking out here. Like we're not actually understanding the concept here. So let's see what dense search is doing. Okay, so now we're getting sentences that kind of are closer to this idea of bad flying. They lack the flight that corresponds to the tumbling flight and the living flight that's not so erratic as black-tailed godwit. So kind of helpful, not super helpful. Bald eagle, this sentence, nope. Like these things are actually good at flying, right? And then we kind of get, we get a result here that is interesting, right? The broad-billed toddy has short rounded feathers that are not streamlined for efficient flight. This is actually a relevant result for us because we are looking for birds that are like not that great at flying. So we'll log these results, kind of doubling there. Let's look at cascading and see what was returned. And we see that the first result from cascading is this result of like, okay, this bird is like not that great at flying, which is really cool. And it looks like this is a double, but I'll go ahead and just mark that anyway. This paragraph is about the young of bird not being good at flying. So it is kind of relevant, but I'll just let that all go. And then we get these other sentences about tumbling flight too. So let's go ahead and log this. Now we can see for the birds that are bad at flying, we can see that dense search didn't do so great. We can see that keyword search got 0 results back here. And by the way, this interface allows us to kind of log all the results we're looking at and edit them. So if we want to go ahead and change their relevance, see the scores, see the chunks that are returned, even the document IDs, we can do that, download the CSV, get an understanding of what's going on here. Creating an interface like this is really helpful for understanding how useful any given search method is for your corpus. So I hope that in sharing this type of demo and kind of sharing this repository, you all can learn about like how to approach these ideas, how to implement these kinds of search, and then how to compare them. And what's great is that because of using things like integrated inference and because of using things that are available on the Pinecone platform, we don't actually need that many external dependencies, especially in terms of model. So you can get started right away kind of building these kinds of search, assuming you have your data set. I'll go ahead and switch my screen back to the presentation, and then we can do our question session. All right, That is what I wanted to cover for you all today. Thank you for letting me present and teach you about different forms of semantic search. I hope you came away with an idea of how to think about different kinds of sparse dense search and how to compose those in order to learn more about how to build these types of systems. And I'm excited to hear your questions. So let's get into it. Let's do a quick question answering session.
Thanks, Arjun. In our Q&A, we do have one question. If you could please take that up.
Yep. And it looks like a lot of people are asking questions in the chat. If you are doing so, please go to the Q&A so we can kind of go over them and talk about them that way. Awesome. Stan is asking a question, what is the advice for chunking strategies for long text? This is a great question. What I've done in this demo is just chunk based on paragraphs, which I feel like neatly encapsulate ideas really well. There's a lot of optimization you can do on chunking strategies, especially based on the types of search that you're trying to do. So my advice would be is to start simple. Use a chunking strategy that allows you to take in as much data as possible and chunk on that, and then optimize from that point forward. I think that if you pick a more complicated chunking strategy at the beginning, instead of kind of working with something and then seeing how far you can get there, that'll be a lot less frustrating experience when you're building these types of systems. Chandani is asking, what is the search type that's used with Pinecone Assistant? How do you change the underlying model for the assistant? Great questions. So to review, Pinecone Assistant is a RAG assistant that you can use kind of out of the box really easily. There are 3 LLMs that you can use with Pinecone Assistant. There's Claude, there's and OpenAI. Actually, those are the 2 main ones. And then on the back end, it uses, I believe, I think it's multilingual E5 large. It's one of the embedding models that we host on our inference platform. That you cannot change. So you can't change the embedding model directly. But the search type is going to be like this agentic search. So what it's doing is it's going to take your input query. It's going to come up with a bunch of queries that could be used to answer that question, run all of those searches in parallel, retrieves the context, and then generates an answer on those contexts. So you can consider it as agentic. And if you want to learn more about what exactly is going on, you can use something called the context API, which will return the retrieved chunks from the Pinecone Assistant that you can expect and kind of understand. The slides will be shared after the presentation, so we'll make them publicly available so you can kind of take a look at what they are. Amul is asking Pinecone versus Neo4j, which is better. These are used for 2 different things. So if I understand correctly, Neo4j is a graph database, which allows you to represent data much differently than a vector database. So we have an article on our website that shows you how to use Pinecone and Neo4j. So if you look for those search terms, Pinecone and Neo4j, I believe it's called Better Together. You can learn about how to use both to kind of build a graph base and a vector database to search over what you're interested in. Hi, Roma. Great question. Cost optimization. So there are many different ways for you to kind of reduce the costs. And I think it kind of determines where you want to kind of reduce costs. So if you have a bunch of text that you're passing to a downstream system, typically that downstream system, like that LLM that you're working with, or maybe that person, reviewing that information is going to be the most costly aspect of that, right? Like the more and more documents you pass to an LLM, the more expensive it becomes to kind of review each of those chunks because you're increasing the size of the prompt that you're sending over. So then it becomes a question of what are the most relevant parts of those documents that I'm sending over that I can only isolate so I can reduce the expense of the whole computation. So that's kind of like step 1 and why re-ranking kind of helps. So if you use a re-ranker, it should increase the quality of your results and then also reduce the number of results that you have to review on average compared to if you didn't use the re-ranker. And that's where cost optimization can kind of come in. And then there are ways of kind of reducing the amount of search that you're trying to do. For example, you can use namespaces or metadata filtering to kind of reduce the amount of things that you're looking for, which will reduce time that it takes to return those results and some costs as well. So it really depends on like where in this pipeline you're experiencing the most cost. And then based on that, you can either change a methodology to make sure you're reviewing less information that's most relevant, or do something else along those lines to help solve that problem. Jagadish is asking, does re-rankers work for each or all of the queries at the same time? So the way re-ranking works is it takes your query at query time, and it takes your document that's been retrieved from the vector database, and it recomputes the embedding. So it's specific to the query and the document that's being computed. And the ranking process happens, the re-ranking process happens if you enable it after a query has been computed. And you could not have re-ranking on every user query if you'd like to, but typically when people implement re-ranking, they do it with all the queries that are kind of coming in. And then what happens is you're only computing the new pairs of the returned subresults and the queries that are coming in. We have an anonymous question about how well it works with unstructured data. This is the perfect strategy for unstructured data, especially data that's like images or data that is text. You want to represent the whole thing in some common vector space and then do just a vector comparison. And because you're transforming everything to that vector space, you can kind of deal with unstructured data really easily. So it's a good fit for things like chat data. Where does the image get fetched from? So what I've done is when I'm scraping the Wikipedia pages, I'm grabbing the first image that is a bird from each of those pages, and I'm storing them locally. So in the application, those images are stored locally, and when we retrieve, I store the metadata of where those images are located in the vector database. And then when I query against that vector database, we can look at the metadata to see what images to retrieve, and then we kind of show what those images are. So we're not searching over the images at all. It's just like a nice way of viewing what birds are returned. But that's a good question there. Madhav Shrutri is asking, does Pinecone work with graph-based RAG? It does, but you have to build a system. Pinecone doesn't work natively with graph-based systems. You have to kind of build your search system that does some search over like a graph database, does some search over Pinecone, and then combines them. So you could do like this sort of re-ranking if that's the way you're kind of going about it. But an example of kind of how to combine those things, we have one on our website. Just search for Pinecone and Neo4j, and you'll kind of come across that example. Rajendra has a great question. I was waiting for somebody to kind of think about this. So Rajendra's question is, if we reduced the doc or expanded the doc, what if we expanded the document with questions and performed the search on the question? So this is kind of like, this is one way of this is exactly how document expansion works, right? Which is like, we take the document, we append these queries, and then we kind of just do a search over that whole document. The reason why it's important to do a search over the whole document instead of just the questions that we're looking for is because when you add the new queries to the document, you're affecting like the count and the importance of those new words to the whole document. And the occurrence and the frequency of the other terms that occur in that document matters to inform what each of those words mean. So if we just did the search over the questions, that's fine. Like you could do question to question search. That's a thing that people implement and that ends up working pretty good, but you're going to lose this property of like understanding how well those words are distributed inside the whole document, which might be important for more complex queries that you want to do. But that is an interesting like modification you can make. And that is a thing that people do. Like think about frequently asked questions sections on websites. That is question to question search because you put in your question, we have a bunch of preset questions and you're just kind of aligning and seeing what is important. But then you lose this property of like understanding what's inside those documents and how that kind of informs what you're interested in. Roma has another great question. Thank you for your questions. Please keep them coming. For non-English languages, does it make sense to translate data to English and then translate back in runtime to increase the accuracy? No, it doesn't make sense to do this if your primary concern is search. The reason why is because if you use something like multilingual E5 large, everything will be represented in the same vector space without you having to do explicit translation. So one sentence is vector and the other sentence is vector, they're in the same vector space, so you can do this sort of comparison. So you can just do this sort of search without having it to be all in English. Like this model has been trained to understand the meaning of these languages, irrespective of like what input language you're using, what output language you're using. That's the crazy part about multilingual semantic search. We have an article on Pinecone on how this works. It's called The Practitioner's Guide to E5. And there's a notebook in there that I wrote that shows you how to do this exact thing that you're talking about, which is if you have an input search in one language and you have a document corpus in another language, how do you find those documents? You can just do this without translation. But if you do translation, you're adding additional latency and you're potentially causing some problems because you might not be able to translate what concept you're talking about in one language to another. Mauricio has a great question. Does namespaces help in these types of searches? Namespaces are great primarily for segmenting your data when there's really hard, strict segments. So for people that might not know, when you're using Pinecone, you can upsert your data or store your data in with something called a namespace, and a namespace creates a really hard partition on your data. Most people use this for like users. So if you have like 10,000 users, they each need their own partition, but you want to store, you want to take advantage of like multi-tenancy and make sure they're getting really performant results back, but you want to store their results so that no one can see other people's results. Like that's when people use namespaces. Or if you have like really different types of categories of things that all are represented in the same vector space, so they're all in one index, but you want to be able to like not search against all of those things at the same time, then you would use namespaces. And then the things that'll help you with using namespaces is that they restrict the search to only things that are inside that namespace strictly, so you can increase the speed of your search. So if you had like books and like movies in your vector database and you wanted to do a search only on movies, you could specify that namespace, upsert everything under movies, and then only do matches against that namespace instead of searching over the whole vector database of like books and movies. That's when you want to use namespaces. That's when they'll be really helpful to you. But any pre-processing strategy that adds a little more information into your corpus, that's going to help you like do this type of search a lot better. All right, these are fantastic questions. Thank you everyone for asking them. We still have some time, so I can keep going. Ahmed is asking a question about multilingualism. So we have an English query, but the user asks this question in AR and EN. Is the search going to work correctly in case the user question wants an AR? So depending on your embedding model, like this will work or this will not work. According to, for multilingual E5 large, which is this like multilingual embedding model, it's designed to handle these types of cross-lingual queries. So you should get better results on average than, or you should get comparable results independent of what the input language you're using. So if you're doing like English to AR or AR to AR or English to English, the results that you're returning back should be pretty comparable in terms of relevance, independent of what language you're interested in. So I would say that would work. But again, like your mileage may vary. Like you should have an evaluation set. You should kind of do what I showed in this demo where you're kind of seeing what the results look like. But my hunch is that would work. How does vector dimensions affect retrieval? Great question. The more dimensions you have, the more parameters you have to do matching on, which can increase latency like non-trivially. You're not going to experience like a latency curve that'll be like really, really big based on the amount of dimensions that you're including, but it'll increase the time it takes to get results back. But at the same time, the more dimensions you have, the more information you're able to avoid compressing, right? So if you had like 768 dimensions versus like double that, like 1500 or whatever the doubling number is, you have twice as many components for you to include information about the query that you're interested in, which means that the quality of your search can go up. So then it becomes a game of like, okay, like what is the most expressive embedding model I can use without imposing too much of a cost on quality. Now, using something like Pinecone is going to really help you because there are algorithms that kind of do this search really quickly for you. So you might not experience that much of an impact going down in vector dimension size. So what I would recommend is use an embedding model that you know works really well. And then once you get to a point where like, okay, I'm pretty comfortable with how well this works, then try to go down and then see what the impact of the quality result is kind of there, right? And you might notice that it'll be pretty big because you're being a lot less expressive. But that's how vector dimensions kind of affect results. It's the quality, usually pretty strict correlation with the quality of the representation, and then the speed of the actual search because you're doing more computation. Yes, Roma, I think the cost has to do with the size of the documents you're upserting. Looking in the chat, Shrikant, you're asking about the code. The repository is public, so you can go look at the repo. It's the Bird semantic search, and then you can kind of see how I've done each of the search methodologies. I've used something called integrated inference, which is this idea in Pinecone where you're just passing chunks to the Pinecone API and specifying the model you want to use, whether it's a sparse model, whether it's a dense model, whether it's best match 25 is a little different. If you specify those models, it'll embed them for you and then upsert them into the index. So the API call is very simple. So if you look at the embed and upsert file in that repository, it'll show you what that actually looks like. Jonathan is asking, working with re-rank, do we need some threshold to limit the vector search results? Great question. The way the vector search result works and the re-rank results work is that you specify the number of documents you want to return. So with the vector search, you might say, okay, find me the 20 closest documents. We call this top K. And then with the re-ranker, you specify a smaller set. You could do the same set, but like most people do a smaller set because you want to optimize the context. You have some context budget, you want to optimize that. So you might say, okay, give 20 documents to the re-ranker and one query. Now give me the top 5. So that would be the threshold that you set. You could say like the number of documents they want to return. That's the most important. So that's how you want to think about it. All right. Any last questions? Any burning questions? If anyone still has questions and we don't answer them in the session, feel free to message me on LinkedIn or find us in the Pinecone community. We're happy to answer any of your questions there. Roma, a few more. I'll answer these last 2 questions, and I think we're just about at time. Prasanta is asking how to evaluate the performance of a semantic search engine. You want to look at latency. You want to think about your business metrics that are important to you. So what problem are you actually trying to solve? And then having some sort of labeling process like I showed in this demo of like what results are relevant, not relevant against common queries. That's going to be the way for you to kind of understand how well these search methodologies are working or not working. And Roma is asking about filtering after re-ranking. Metadata is your friend here. Any other attribute about the data that you can find important to the user is your friend here. Okay, I think we are just about time. I hope this session was really helpful for everyone, and I hope you enjoyed it. If you have any more questions, feel free to find us on the Pinecone community or to message me on LinkedIn.
Right. Thank you so much. That indeed was a wonderful session. On behalf of Analytics Vidhya, thank you for your time and for delivering such a wonderful session. Our audience found it insightful, and we really hope we can conduct more such sessions with you in the future. And for those of
Awesome.
you who would like to connect with the speaker, I've shared Arjun's LinkedIn profile in the chat section. Please feel free to connect with him. And I request all participants to fill in the feedback form before leaving so we can make our sessions more interesting and even better for all of you. All right, then. Thank you all. Have a great evening.